So today we're going to look at a pretty complex two-dimensional motion problem. It's a projectile motion one. And this one's going to have a few interesting things that go along with it. At least I think they're interesting. You might not agree. So first thing I need to do is unfreeze my board. But we're going to set this up as a theme problem. Now, the initial theme is the following. Many of you are planning on going off to college. And the first thing that I can give you as a piece of advice is please, 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 please sign up for as many scholarships as you can. Fill out for federal funding. Do whatever. Speaking as someone who graduated a very long time ago and still paying off student loans, seriously try and get as much money as you actually can. And I didn't just take out loans during school. I actually worked the entire time I was in school. It can get expensive. If you find yourself in the position that you actually need to work in school, you might end up with a job similar to this. You might not. I don't actually know how hard it is to get. But let's say that there is a concert. People jamming out to a concert. This person is not having a particularly good time. Partly because I haven't connected his body completely, but not really enjoying things as much as the other concert goers. You might end up with a job, something that I call, although this is probably not the appropriate title for it, a crowd wrangler. And you will be armed with a t-shirt cannon. Your job is to make certain that they are happy. And if they do not look like they're going to be happy, you are going to fire a t-shirt at them because who isn't happy when things are flying through time and space at them at high speed? So this is a concert of some kind. That's what instruments look like, right? All right. What I can tell you is this. You are down here on the ground level, and the person that you are actually aiming for is some height 3 meters above where you are, at least where your t-shirt cannon is. Now, you, as an employee, have gone through and read the materials that tell you how to operate your equipment. It's a t-shirt cannon, and your instructions tell you the following, that the cannon will fire the t-shirt at an initial velocity of 20 meters per second. That's about 45 miles per hour. Not a small amount. We've got some heft with this, hence the cannon. And you have a shoulder-mounted cannon firer that will always fire with 55 degrees above the horizontal. Now, the question is, because you want to get the t-shirt to this person, how far back do you need to stand? You could fire from here or back over here, or you may have to come forward. We don't know, but what we do know is we want this person, the person who is not having a fun time, to get a t-shirt flying directly at them because they will either have a good time or else. So, that's what we're looking for. Now, this starts off as a ham-fisted, okay, I'm not actually going to have a job where it is exactly this. What this could actually be instead is you being an engineer who's designing a t-shirt cannon for minimum wage workers to actually then fire at other people. So, don't get too caught up in the ridiculousness of my scenario. Remember that there is something that could actually be very realistic about this. Depends on how you look at it. Either way, we're going to take a look at this particular problem. How far back do we need to stand? Well, we're going to have this t-shirt moving through time and space, and it's going to fly through the air. So we're going to end up with a classic two-dimensional motion problem. When I do that, I fully recommend writing out the table for all of our values. Just like I've taught you, hopefully, in class. Now, this concert is actually going to be here on Earth, though I don't know, at the rate we're going, maybe you'll be going to Mars University, Robot House. So, maybe you'd have to adjust this. Here on Earth, the acceleration in the y direction will be negative 9.81 meters per second squared, or something very close to that. If you were doing this for Mars, the acceleration due to gravity, I think, is negative 3.63, something like that. At least that's the standard value on the surface of Mars, if I'm not mistaken. So maybe you'd have to go in and design a different T-shirt cannon for a different planet. Who knows? I think colonization's been put on hold for a little bit. The T-shirt itself has no engines or rocket powering, so we accelerate it in the cannon and then let it fly through the air. Its acceleration, like many things flying through the air, the acceleration in the x will be 0 meters per second squared. We're ignoring air resistance, which makes it a little less realistic, but that's okay. And we don't have powered flight, so this would not apply necessarily to a plane, for instance. They have engines, but they could have an acceleration in the x. All right, let's see what other information we know. We do know that we are going to try and get this T-shirt up 3 meters. So my displacement in the y is positive 3 meters. I've got a system that's implied here, but let's go ahead and lay it out. I'm using the standard coordinate system where to the right is positive x and up is positive y. All right. I'm going to need more information. First things first, though, what am I looking for? Well, ideally, what I'm looking for is the same thing we're often looking for, but not always. My displacement in the x. I'm effectively trying to find the range for this setup. I'm going to need more information on this, though. So the other thing that I have not looked at yet is the initial velocity. Well, we're going to take this. We know that it is v0 equals 20 meters per second. It is at 55 degrees above the horizontal. That means we will have an x component, v0x, and we will have a y component, v0y. This is some of that vector stuff that we dealt with before. I realize that I have moved my calculator. Oh, there it is. Be right back. Haha! Calculator. All right, let's see. So I'm going to quickly do this. If you need some help with vectors, I've got some other videos on that, but we're going to be using a cosine function, 55 degrees. Good, I'm set to degrees. Great. Times 20 meters per second, and I find that my initial velocity in the x direction is about 11.5 meters per second. There we go. All right. And then my initial velocity in the y, well, that would be sine of 55 degrees, because that's the opposite side, times 20. I end up with 16.4 meters per second. Now, as a brief reminder, that may not match with what I've drawn. I'm lazy and almost never draw things to scale. With this being 55 degrees, the opposite side should actually be the longer one. All right. And that's what we actually find, so that's good. Okay, now that we found some information, let's fill it back in our table so that when we do more work, we don't lose that information. We found v0 in the y was positive 16.4 meters per second, positive because it's going up at the very beginning. And over here in the x, 11.5 meters per second. Now, real quick, this isn't a thing that you have to do, but since our acceleration in the x is 0, if this is my initial velocity in the x, it's also my final velocity in the x. Now, you may think that you've got 3 pieces of information you can directly solve for the fourth, delta x, but you'll find that with the equation that you have to use, you have to divide by 0 and the whole thing will just explode. There are actually other reasons why you can't find anything out on this. I'll go ahead and mention the main one. There's no limiting factor here in the x direction. This says that it never speeds up or never slows down. The acceleration is 0. So basically, the numbers that we're giving it have an infinite number of answers. Delta x could be anything, and we multiply it by 0, and we'd still end up with the other 2 things being equal. The equation still works. We can't solve for anything because we have no limitation. That just says that it will keep moving forever. Well, it would if it weren't for the fact that gravity is pulling it down, and eventually it's going to hit the ground. Our limitation in this problem is the fact that we'll fire it up and then it will fall down and eventually hit a person or a thing. It can't go on forever. But if you think about this, none of the information here in the x actually gives us a limitation. It will always have this initial velocity, always have that final velocity because our acceleration is 0. So that's every single point in the x direction that my t-shirt does. There's no way for me to select out one individual part of its flight because this applies to all of it. We need the y direction to give us information about what point we're looking at. We're looking at the point when it is 3 meters up in the air. All right. So in short, we cannot solve the x direction with just this. All right. So we want to take a look at the y, and we can find the time that it will take to get the 3 meters up, and we'll see how far it goes in the x so we know how far back to stand. All right, so we come over here. We want the time, so we are going to use the 3 pieces of information that we've got and get that set up for the time. Give me just a moment. Okay, just checking the camera. I'm a little paranoid because this is the 3rd time I'm trying to shoot this video. I've been having some camera issues. If we use the equation that we need to go straight for time, we'll use the following. It's the most common one that shows up a lot. It is delta y, or delta x if you prefer, equals v naught in the y times time plus 1/2 ay t squared. We can fill in our values. We've got positive 3 meters equals 16.4 meters per second times time plus 1/2 negative 9.81 meters per second squared times time squared. Now, what I don't like about this is a quadratic equation, which means we've got a couple of options. Now, the first thing that you can do, and many of you may be already singing the song and dance number that goes with it to get the quadratic formula. B squared minus 4ac all over 2a. I can take this equation and I can put it in the more standard form that does the following. Let's see, I'm going to do a little bit of algebra here. You're welcome to follow or do this on your own. 1/2 times negative 9.81. I'm going to add that over to the other side. We should get the following. Positive 4.905 meters per second squared. That's 1/2 times 9.81. The negative, I'm adding it over to the other side, times t squared minus 16.4 meters per second. I move this one over to the other side by adding it. This one I must subtract. Times t plus 3 meters equals 0. This one's already over on the other side, so it stays positive. If I remember correctly, this is my A, this is my B, and this is C. We can plug those in here, and you can solve for them. Now, when you do that, I'm going to give you a heads up on this. I don't usually do the quadratic equation approach, but you are more than welcome to. There are 2 answers to the quadratic equation, and in most of the problems that you work with, one of those answers will be negative. One of them will be positive, and you all have been trained very well to go with, oh, it's the positive one because the negative one doesn't make sense. This is an instance, this particular problem, both of the answers you get from the quadratic equation will actually be positive. In fact, let's check it real quick. Might as well while we're here. I'm going to fill these in. Let's see what I get. Negative b, which is, remember this is normally a plus, so b is actually negative 16.4 meters per second. Negative b plus or minus the square root of b squared, negative 16.4, quantity squared, so the negative doesn't actually matter there, minus 4a, positive 4.905, c, 3, all over 2 times a, which is 4.905. There's some units that go along with this, but for now, I'm going to keep this a little bit simpler. Let's see what we get. 16.4 squared, technically negative, minus 4 times 4.905 times 3. I end up with everything under the radical comes up to 210.1. I take the square root of that, and I get the following. I get negative and a negative. This is a positive 16.4 plus or minus the square root of 210.1. So plus or minus 14.5, 14.494, so 14.5 divided by 2 times 8, 9.81. All right, so the two things that I get, this will be t equals, for our case, the two things that I get, if I take 16.4 minus 14.5 divided by 9.81, one of them, t will equal positive 0.194, well, I presume seconds. We could check the units. I'm being a little lazy with the units. Or we could get 16.4 plus 14.5 divided by 9.81. And we end up with 3.15 seconds. As I said, this is a problem that many people may not have encountered, but both of our answers from the quadratic equation are positive. So which one is our answer? First, let's talk about why you have two answers. I told you that we've asked about a limitation. We came in and we're looking in the y direction, and when we put in that delta y will be equal to 3 meters, we're saying when the t-shirt is 3 meters above where it starts, with this information, it starts off this fast with this acceleration, at what time does that happen? When is the t-shirt 3 meters above its starting location? I want you to stop and think about this. Let's ignore the rest of what's out there. I fire the t-shirt, and what's it going to do? It's going to go up and come crashing back down in a parabolic shape. It actually is a parabola. Now, if we're talking about some height 3 meters above our starting location, well, that happens right here. And it also happens over here. This is why there are two positive answers, because there are 2 times that it's actually up 3 meters in the air. The first one happens about 0.2 seconds after we fire. It takes about 0.2 seconds for it to get to this one. The other one happens about 3 seconds after we fire. There are 2 answers. What does this mean? Well, you have 2 options. You can either get up close and have, let's see, I'm actually going to draw the arc here. We're going to fire the t-shirt and it goes off like that. Not my best arc ever. Let me redo that. Put that out of the way. Let's say that we've got it going up like that. Great. That way it's a little more visual. The 2 things I could do, I could try and have him catch it on the near side here. That means I get up real close. There's a downside to that, at least with my hand-wavy drawing, because remember, I never really draw stuff to scale. In order for this guy, this person, I should say, to get their t-shirt and be happy, this person ends up with a t-shirt to the chest, and then it has to fly through them. Don't think about that too hard. So we might instead have to come out over here where they can catch it. Maybe I have to stand right up against here. Now, there are a couple things to keep in mind. I just randomly drew this. Maybe there isn't enough room to get that far back. Maybe this row isn't that far forward. In short, if this is not you being a part-time job person, but you designing a t-shirt cannon for venues to use, this is exactly the sort of thing that you should consider. This might not be the best one because we're going to t-shirt that person directly in the head. In short, why are there 2 positive answers? Because there are 2 possible answers to what we've asked. We could either have them catch it on the way up or catch it on its way back down. I don't like doing the quadratic approach, so I'm going to show you what I do instead of the quadratic approach. Here's what we're going to do. If you take this information, I'm going to get rid of this. We solve for a time at which we're at a height of 3 meters. If I try and go straight for the time, I have a quadratic equation. And now we know why there are 2 answers. Particularly for this one, there are 2 positive answers. But one of the things I can do is instead of going straight for the time, let's go for the final velocity. One of the things that I'll follow up asking you on this is, how fast is the t-shirt going when it gets to that person? Because if it's going 80 miles per hour, that's going to be bad because that t-shirt will probably hurt someone. Now, if it's going more like 20 miles per hour or maybe a nice 10 miles per hour, that would be pretty good. So that's another thing that's a real-world consideration that we would actually want. And if you are asked for the impact speed, you will need the final velocity anyway, so it may not be a waste of time to take this extra step. If we do that, we get the following. I'm going to use the equation that does not have time, plus 2ay delta y. I'm going to fill in my variables on that. We'll be back in just a moment. Okay, just double checking the camera. Like I said, I'm a little paranoid. All right, so I fill this in. We're solving for v1y, our final velocity in the y direction. Our initial velocity in the y was 16.5 meters per second, quantity squared, plus 2 times negative 9.81 meters per second squared times delta y, which was positive 3 meters. All right, I'm going to multiply some of this stuff out. We get v1 final squared equals 16.5 quantity squared is 272.25 meters squared per second squared. We square the value and the units, plus 2 times all of this stuff. Let's do 2 times 9.81 times 3, 272.25. Let's see. Minus 58.86 meters per second squared times meter is meters squared per second squared. Great, all of these have units of meters squared per second squared, as they must. They all have to have the same units. All right, double check. Oh, I'm sorry, not 16.5, it's 16.4. Bad Sanchez. 16.4 x squared. Let's double check that. This is why it's nice to have all of your values filled in. Yep, 16.4. I apologize about that. You're not 272.25. Get out of here. You are 268.96 minus 58.86. And I get v final on the y squared equals 210. Whoa, wait, why does that sound familiar? Meters squared per second squared. That sounds really familiar. All right, let's find our final velocity, familiar or not. Okay, so I'm going to take a square root to get rid of that squared. And here we go. I'm going to do v1 in the y equals square root. Answer is 14.5 meters per second. Those are my units. Wait a second. 14.5. Well, that's a speed, so that'd be meters squared per second squared. That had meters per second squared and meter. Oh. This part of the quadratic equation gave me the value that I just found. That's exactly the same amount of work. We now found that our final velocity in the y is 14.5 meters per second, but wait. The last step that we did was a square root, so it could be positive or negative. Which one do I want? Well, it depends. If I want the positive one, my final velocity would be when it's going up, and that corresponds to me trying to get them to catch it on its way up. If I go with the negative, that's me trying to get them to catch it on the way back down. That's what that means. I actually have 2 options in this case because both of the velocities could apply to my scenario. In this case, we're going to say that we're going to go with the one farther back, so that way we're not firing a t-shirt through this poor individual. So I'm going to finish this up and say, okay, we're going to say that they're going to catch it on the way down, and its final velocity is negative 14.5 meters per second. This looks a little bit different, but it's actually the exact same amount of work as solving this part of the quadratic formula. In problems where you only have one answer, you'll need to remember, say for instance, that we're looking on the far side when our final velocity is negative. But that allows you to choose between the positive and negative. You don't have to check both of them if you know what your problem actually is. You can take a look at some of my other videos that details this same approach. But I wanted to try and get that across here. This is an instance where both of our answers are positive. And now we can understand what's going on with that. Now that we've got this, it's actually the exact same amount of work as doing the quadratic formula anyway, so you're welcome to do that if you'd like. But this allows us to fill in something that the quadratic formula wouldn't have given us. So if they ask us for more information, we've already got part of it done. Okay, so I'm going to go through and finish this up. Let's solve for the time for them catching it on the far way down. I am a profoundly lazy person, so let's go with the simplest equation. V final in the y equals V initial in the y plus acceleration in the y times time. Well, V final in the y, we said was negative 14.5 meters per second. We're doing it when it's on the way back down. If you want to aim for cutting through that poor unfortunate person with a t-shirt, then your final velocity would be positive. That would be on its way up. Equals our initial velocity in the y, which was 16.4, not 5, get with the program, Sanchez, plus negative 9.81 meters per second squared times time. All right, we do some math on this. Subtract this over to the other side, so we have 14.5 plus 16.4, technically negative 30.9 meters per second equals negative 9.81 meters per second squared times time. Divide those sides by negative 9.81, and we get that time equals, hey, look at that, positive 3.15 seconds. We chose the velocity for on the way back down, and we got that same time that we found from the quadratic equation. If we had gone with the other velocity, the one that is on the way up, then this equation would give you the other one from the quadratic equation, the positive one. The nice thing about this is we're filling in some additional final information that we might or might not need, and honestly, it is no more mathematical work than this. On top of that, many times we can also save ourselves some trouble by knowing whether it is positive or negative. This is one of those circumstances, one of the few ones, in which you can't actually know which one is positive or negative. It depends on how you design this, what you actually want to solve for. There are two positive answers. All right, now that we've got this, we're aiming for the one where we're not sending it through this poor person, at least according to my not scale model drawing. We might actually find that the other one is a better one to use. 3.15 seconds. Now that we have that, this is 3.15 seconds, and we can go through and we can finish this up. We'll find that I will need to stand 36.2 meters back. That's like 100 feet. You might be able to fit that in here, but now maybe we need to go through and do the other one. The other one would be, well, 0.194 times 11.5. I hit a button. 0.194 times 11.5. The other one would only require us to stand 2 meters back, so we could get much closer here. So you might actually, I like the idea of them catching it on the way down and not hitting this person in the face, but maybe we don't have that room. In either case, what we're actually now coming face to face with is we may want to redesign this launcher. It may not be able to fit in the standard venue. All right. The last thing that I want to mention is this. Why is it there are two positive answers on this? Well, the classic question that you'll probably end up with instead is having something where it's on a cliff, where you have maybe a cannon or something that then fires something off like this at some angle theta. Now what it'll do is it'll fly up in the air and then come crashing down to here, and when you solve for a delta y of, let's say, negative 30, when you give the equation that information, it's looking for the time at which the object is at negative 30. Well, one of them is here. Time equals a positive number. Not my least confusing choice ever, but it'll be a positive number because time equals 0 is when we fire it. That's how we've set it up. But the math equation doesn't realize that. The quadratic equation doesn't think. It doesn't know what a cliff is. It doesn't know what a cannon is. It knows what quadratics are. And a quadratic would be an equation that keeps on going like this. It doesn't know that the object stops here because there's a ground there. All it does is say, okay, well, this is one of the places where your delta y would be equal to negative 30. This happens after time equals 0 here. When you give it information, the equation thinks that the projectile starts way down here, is flying up this way, goes all the way around, and goes way back down over here because it doesn't know that there is a cliff there. The negative value is the other point when delta y equals, say, negative 30. Except this happens because the equation thinks that it's going up like this. This happens before time equals 0, so it will be a negative number, meaning that it's before 0. That's what the other one means. That's why in regular ones you'll have one positive and one negative, and the positive is usually what you're looking for because the negative makes no physical sense. In this problem that I gave you, both of the times are things that can happen, and therefore we got two positive answers. We'd have to go through and choose between them. This is a more complicated projectile motion problem, especially in that if you robotically go through using the quadratic equation and say, well, the positive one's the correct answer, you've got two correct answers. And it's important to understand what these equations are giving you so that you can do more than simply solve the problem. You can understand what you're doing.